Okay, Calc students, this is section 3.7. I don't know how long we will be learning remotely, so I'm going to kind of keep looking at each section separately and determining whether I think it needs a lecture recording or whether I think there's enough information in the PowerPoint slides for notes that can get you by. This one I decided to do a recording because the PowerPoint notes were kind of all over the place. I, I'm going to attach them to your Google Classroom posting for this assignment, but they just had lots of different statements and different directions they were going in the PowerPoint slides that were not manifested in the assignment from Missouri Valley. So this is a sampling of your homework problems for your assignment for 3.7, which is rates of change. We're talking about like in the natural sciences and physics and that kind of thing. So this is kind of where these derivatives get put into practice, okay? So let's take a look at these. I'm not going to be solving these problems in their entirety in most cases, but kind of talking you through them. Some of them have watch it, some of them don't. But anyway, this is the application that I know some of you guys have been asking for when it comes to derivatives. So this is number 1 in your WebAssign homework. A particle moves according to a law of motion, and we know that S is kind of our position function, right? And so it says S equals F of t, so that's our position function. T is, of course, time, and in this case, it's measured in seconds, and S is measured in feet. So they give us our F function, which again is our position function, and it says find the velocity at time t. Well, we know, again, let me just remind you that acceleration is the derivative of velocity, and velocity is the derivative of the position function. Okay, so acceleration is like the double derivative of the position function. Velocity is the first derivative of the position function. And then you have acceleration. So anyway, just kind of a reminder. So velocity is the same thing as f prime of t. You are finding the derivative there. Okay, so in this case, that is going to be what? 3t squared minus 24t plus 36. Obviously, I can't get it to all fit in the box there, but that is your derivative. Okay, and that's velocity. Velocity is the first derivative. Acceleration is the second derivative. Okay, so then it says, what is the velocity after 3 seconds? All you're doing is plugging 3 in to the v function that we just found. Okay, now, when is the particle at rest? The particle is at rest when the velocity equals 0. So you need to set your velocity function, that first derivative, equal to 0 and then solve for t. And notice they give you 2 different values, which should be correct because if you look at our velocity function, we have a t squared. So we should get 2 different values for t. Okay. I'm not going to solve that for you. I'm just going to tell you the particle is at rest when velocity equals 0. It says, when is the particle moving in the positive direction? The particle's moving in the positive direction when v of t is greater than 0. When your velocity is greater than 0, you are moving in the positive direction. So once you figure out what interval that is, it says enter your answer in interval notation. First, if you figure out when the particle's at rest, by figuring out the problem above it, you'll figure out your interval, your your solutions for t, then that will cut your domain into intervals, okay? And then you can test those intervals to figure out which one's going to give you a velocity that's greater than 0, okay? Again, I'm not solving these for you. I am leading you through them, okay? So particles at rest when velocity equals 0, particles moving in the positive direction, okay? Positive direction when velocity is greater than 0. So you all know how sometimes we have found the velocity to be negative. That's when it's moving in the negative direction. So part E says find the total distance traveled during the first 8 seconds. Okay, so you are going to have to find the distance traveled in the intervals separately. So you're going to have to figure out how far it traveled in each of 3 different intervals. Okay, that's my hint to you. And then add those up. All right. And then it says find the acceleration. I need to clear this and scroll up. Again, I'm not solving these for you. I'm walking you through them. Find the acceleration at time t. I think we all know that acceleration, I had written a little bit ago, acceleration is the derivative of velocity, or it is the second derivative of the position function. So you're going to take the velocity function and find acceleration. And then it says find the acceleration after 3 seconds. So obviously after you find the second derivative of the position function, our s or f in this case, then you plug a 3 in. Now, I just want to remind you here on these. On part G, graph the position, velocity, and acceleration functions for the first 8 seconds. A lot of this is going to depend on what you solved for t, okay, in that first, what section was that? Part C, I think, okay? So part C, remember, is when your velocity equals 0. Now remember, if velocity is your first derivative, that means your s function, that's when your s function either equals a local min or a local max, where the slope of the function would be 0, or where that s function would change directions. Okay, when the s function change, like just for instance, the second one over here. This s function here, velocity should be 0. Here, velocity should be 0. Actually, as I say this, I notice it is. So that's your position function. Velocity should be 0 when you have a change in your direction that your position function is going in. Okay, I hope that rings a bell from back when we first started talking about derivatives. And then here, this other purple dot, again, it changed direction. That was a local minimum. Okay, when it changes direction, that black position function, that is where your derivative should be 0. Now, the other thing you notice is as you travel along this black position, this slope of the tangent line on all of these points is going to be positive. So your velocity should be positive. Okay, so from 0 to here, velocity should be positive. Okay, now I'm not saying this is the graph. I happened to look up at this one. It was still on the board, and so that's what I was looking at. This side of it, if you graphed your tangent line as your position function is going down, the velocity, the derivative should be negative. Okay, and again, derivative after we make a change in direction should be positive. So as I kind of traced that black position line function, you can kind of see that for velocity. Okay, and then I'll let you figure out again that acceleration is the derivative of velocity. So if you were going to do the same rationale then, if you were tracing your velocity function, where your velocity function changes direction, like right here, your acceleration function should be 0. Okay? And again, all of these, if I'm tracing my velocity function, all of my tangents would have a negative slope. So your velocity should be below 0. And then after I make my turn, all of your tangents here should have a positive slope. My velocity should be positive. Because remember, or sorry, my acceleration should be positive. Remember, acceleration is the derivative of velocity. So you use the same rationale as you kind of trace the position function and find the first derivative of velocity that goes with it, then as you trace the velocity function and find the first derivative of that, which is acceleration. Okay, so just wanted to kind of remind you of those. Okay, now a couple of other things. It says, when is it speeding up? When is it slowing down? So here's what's important here. When it is speeding up, okay, what do we know? We know when it's speeding up that v and a, the velocity and the acceleration, have the same sign. So when the particle is speeding up, velocity and acceleration have the same sign. So once you correctly pick your graph, you can pretty much find the intervals then on when the particle is speeding up or slowing down. Now I will say on the PowerPoint, they go through an example like this. The first part of the PowerPoint I think is fine. And the very end of the PowerPoint I think is fine. It's the stuff in the middle that's kind of goes off the rails a little bit. But they do have a good example in the PowerPoint of this towards the beginning. So velocity and acceleration have the same sign when the particle is speeding up. Okay, so slowing down, obviously you can about guess then velocity and acceleration have different or opposite signs. Okay, so when the particle's speeding up, velocity and acceleration have the same sign. That means they're both positive, both negative. When it's slowing down, velocity and acceleration have different signs. Okay. Again, I'm not going to solve these for you, just wanting to walk you through them. And this has a watch it too. But now it says graph the velocity functions of two, or the graphs of the velocity functions of two particles are shown where t is measured in seconds. Now it says, this part A, when is the particle in figure A speeding up? Now again, we just got done talking about it's going to speed up when velocity and acceleration have the same sign, okay? Either both positive or both negative. Now, something I want to point out here. Let's kind of, based on the graph of the velocity function there on this top one, let's kind of figure out what the acceleration function would look like based on what the velocity function is. So first of all, once again, right here, my acceleration function would be 0. If I was going to graph acceleration, I'll use blue here, that would be 0 because that's a change in direction. Okay, and it looks like right here, it might also be 0 because it looks like it's getting ready to come back up. Now, from here to here, okay, from here to here, the slope of my acceleration, my first derivative would be positive because as I trace that velocity, that first part of the left side of the hump there, it's going up. Okay, so my acceleration would be positive. So that means I don't know what it would look like, but I know it would be up here. Okay, and then I know it's going to have to come back to 0. Now, from here to here, that was bad drawing, but it's going down. If I trace this velocity function, let me get red. If I trace this velocity function, my derivative, my slope is negative. So I know that between here and here, at some point, my acceleration is going to have to be in the negative region. Okay, so if I'm just graphing acceleration, I know from here to here is going to have to be positive, and from here to here is going to have to be negative, and here it's going to have to equal 0, because that's where I have a change in direction in the velocity function. Okay, so just based on that, it says, when is the particle in figure A speeding up? Well, again, speeding up is when velocity and acceleration have the same sign. So the first thing I see would be the interval 0, 1. 0, 1, I know it's going to have to be speeding up. And we don't include the endpoints, okay? Just FYI. And then when else would it be speeding up? So again, have the same sign would also be from here to here, right? They're both negative. So this would also be from 2 to 3. They would have the same sign. So then when is the particle in figure A slowing down? When do they have opposite signs? Well, they have opposite signs here from 1, you can kind of tell, to 2. The acceleration's negative, but yet your velocity is positive. So that would be from 1 to 2, they would be slowing down. Because again, slowing down means that velocity and acceleration have different signs. Okay, I hope that's helpful. All right, kind of moving through. I'm not going to do the next one for you. Let's look at number 3. Number 3, it says the height in meters of a projectile shot vertically upward from a point 2 meters above ground level with an initial velocity of 23.5 meters per second is blah, blah, blah. Okay. And again, when we're talking meters, this 4.9 is pretty standard on the squared term. It says after t seconds. Now, round your answers to 2 decimal places. Find the velocity after 2 seconds and after 4 seconds. First of all, let me kind of draw a picture. So this is an inverted parabola, essentially, right? It's a squared, it's a quadratic function. So if this is ground level, okay, someone is 2 meters up, and he's going to shoot something that goes up and then comes back down. Okay, so this is 2 meters. All right, sad drawing, but you get the idea. First of all, find the velocity. The velocity is the first derivative of h. Okay, they gave us the h function. It's actually the height, but it's the first derivative of h. So you can figure that out. Then plug in the 2 and the 4. Okay, that's how you do that. Now it says, when does the projectile reach its maximum height? There's a couple of ways you can actually do this. Okay, so this is our h, this is height, and this is time, essentially, if we were graphing this. Okay, vertical is height, obviously the horizontal axis would be time. When does the projectile reach its maximum height? Now, I don't know if you guys remember like the vertex form of a parabola, okay, but x equaled like negative b over 2a. That gave you the x coordinate of your vertex. Okay, the other thing that you can do here is it's going to reach its maximum height when the velocity is 0. So once you solve for velocity, once you find that first derivative of the h function, of the position function, set it equal to 0 and solve it. Now, if you solve this, it's a quadratic, but once you find the velocity, you get down to a linear function, right? So when you solve it, you should only get one value for t. That's why there's just one box, okay? So the velocity, when it equals 0, that's its maximum height. And how do we know that? Again, that's maximum height is right before it takes its turn and comes back down, right? So if I'm tracing this, this is positive, 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 positive velocity, and then negative, 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 negative velocity as it comes back down. Okay. So what is the maximum height? Well, once you find the t for the maximum height, once you've solved part B, you plug that value in to the original position function to find the maximum height. Okay, again, if you think of this in terms of solving the quadratic, instead of thinking of this in terms of derivatives, you are trying to find h of the negative b over 2a. Okay, that would give you your maximum height. All right. Once you figure out what the x is, the x coordinate, if you will, of the vertex, in this case, it's kind of the t coordinate of the vertex, but you plug that back into the position function to figure out what the maximum height is. Then part D, when does it hit the ground? It hits the ground when h equals 0. Okay, so set your original position function, your 2 plus 23.5t minus 4.9t squared, set that equal to 0 and solve. You're going to have to use the quadratic formula. Okay? Quadratic formula. I hope you all remember quadratic formula. Quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Hope that rings a bell. Okay, you're going to have to use the quadratic formula. And again, this is your a, this is your b, this, of course, is your c. Okay, the a includes the negative, by the way, don't forget. And then part E, it says at what velocity does it hit the ground? Well, once you solve, first of all, it says when does it hit the ground? If you're solving a quadratic, what's going to happen here? You're going to get two values for t. But t is a measure of time. You're probably going to get one positive and one negative. Well, obviously, can we go back in time? No. So we ignore the negative answer. Okay, so once you find the t here, so the answer from part D goes into the velocity function, okay, to solve for part E. So once you figure out, because think about what that means, okay, when you solve for time, that means that it's going to be the time that function equals 0. And the reason why we don't have it over here is because we shot this sucker from 2 meters up. If we continued the parabola, it would be on the back side of the person. Again, that would be a negative t. That's why we ignore that one. Okay, we shot the projectile from 2 meters up, and so it shot up and out. So we just need the time that it hits the ground. So at what velocity does it hit the ground? You take the time from part D and then plug it in the velocity. Okay. All right, hope that is helpful, kind of talking you through these. I know you all would love me to just solve them for you, but I'm not going to do that. Let's look at number 4, which is extremely similar to number 5. So if I just kind of talk you through number 4, you should be fine on 5. Find the average rate of change of the area of a circle with respect to its radius r as r changes from 3 to each of the following. Now, first of all, area of a circle, we know, is pi r squared. Okay, so it says find the average rate of change. Now remember, average rate of change with respect to its radius just means it's slope. Okay, anytime anybody says rate of change, it's slope. So we're going to compare the difference in areas divided by the difference in radiuses on bottom. So this is the area of 4 minus the area with a 3 in it over the difference in actual radiuses of 4 minus 3. So this is pi r squared, which would be 16 pi minus 9 pi, 3 squared pi over 1, which is 7 pi. That would be my answer on part I in A. Okay, does that make sense? So you're literally finding, maybe I should change how I write the area here. This is area with respect to radius equals pi r squared. Okay, so you're finding the area with a 4 radius minus the area with the 3 radius over the difference in radius. Because again, rate of change is just slope. So we're doing the change in area over the change in radius. Same thing here. I'm not going to finish it, but we're going to find area with the 3.5 minus area with just a 3 over 3.5 minus 3, and then solve that. Okay, same thing with the one below. So then it says find the instantaneous rate of change when r equals 3. Instantaneous rate of change is derivative. Okay, instantaneous rate of change is like velocity. Okay, it's the first derivative. So if a of r equals pi r squared, what is a prime of r equal? It's 2 pi r. Okay, that's the derivative. Okay, again, we're finding the derivative with respect to r. So we drop the 2 down in front. Pi is just like a constant hanging out the front. So 2 pi and then r. Okay, and then you just plug a 3 in, which should be easy enough. Okay. So 5 is very similar. It just deals with surface area and it gives you the formula. This one looks way more complicated than it really is. This is not a big deal. You just want to find d prime. Okay, how fast? Again, we're talking rate of change. Okay, how fast would be rate of change, which is the derivative. So first you want to find the derivative with respect to t. Find it first, and you're going to have to use the chain rule. Okay, so 5 times the cosine of whatever, the first derivative or the first step of the derivative in the chain rule would be -5 times the sine of whatever, and then you take the derivative of what's inside. Okay, and then you plug in, it says how fast was the tide rising or falling at the following times. So the key here is that time t is in hours after midnight. So here your t is going to be 3. Here your t is going to be 6. Here your t is going to be 8. And here your t is going to be 12. Okay, because the key was time t is in hours after midnight. So first find the derivative, going to have to use the chain rule. Okay, and then, well, I say I'm not going to do it. Let me just start it. So you've got -5 times the sine of all of this. And then the chain rule tells me, first of all, the derivative of 7 is 0. That's why I just left it off. Excuse me. And then you have to find the derivative of what's inside the bracket. Okay. Well, again, if you distributed that what's inside the bracket, that would be a 0.503 t minus some constant. So we can ignore the constant because the derivative of a constant is 0. But the 0.503 times t means I am also taking this times 0.503. Okay, so that's the derivative. You could make it prettier by taking the -5 times the 0.503. But that's essentially the derivative. okay? Then you're just plugging in t equals 3, 6, 8, and 12. Not a big deal. Okay. Okay. Population of bacteria triples. Anytime they say that a population doubles or triples or quadruples, that is giving you the base number. So anytime you're coming up with a formula and you need an exponential function, it starts with the initial amount, okay? So it starts with an initial amount times some base. In this case, because it says it triples, my base is going to be a 3, and then up here is always your time. Your time is in your exponential spot. Okay, so that's like always the case. Okay, that's how you find exponential functions. So again, if it said it doubled every hour, the base would be a 2. If it said it quadrupled every hour, the base would be a 4. And T, I should say, is time in hours, since it said it tripled every hour. Anyway, so in my initial bacteria is my 300. That goes in for my N sub 0. That's my initial amount. So my original formula would be 300 times 3 to the T. Now again, that T only applies to the 3, not the 300. Okay. Then it says, use it to estimate the rate of growth of the bacteria population after 1.5 hours. Okay, after 1.5 hours, you have to find first the derivative of n. Okay, use your cheat sheet I gave you. I just want to remind you that the derivative of b to the x equals b to the x times ln of b. Okay, just want to remind you of that. So that's how you could help find the derivative of n. Then once you find the derivative, you plug in 1.5. It's literally as easy as that. Okay. And then there's really just one more problem here. This thing got longer than I thought it would, and I don't even know that you really need me to help on number 8. Actually, I don't think you do. I think I'm going to leave you to it. Now, I will say, if you need some help here with number 8, there is an example at the very end of your PowerPoint that goes over cost functions, but marginal cost function, again, you can tell here, is the derivative. Okay, and so they're talking about the cost of producing so many yards of fabric. So the cost of producing the 401st yard of fabric, you find the marginal cost of the 400th yard of fabric. So I kind of gave away the answer on this one, so I shouldn't have said that. Anyway, again, they've got a pretty good example of this at the very end of the PowerPoint. So hope this is helpful. Hopefully we can get back to class sooner rather than later, but I will continue to record lessons if I think you need it. Okay, again, I've got office hours, so make sure you're checking your email. I emailed all of you about regular office hours if you need me. Okay, good luck, and if you need me, holler.